All right, to find the vertex of the quadratic, this is the first thing you need to do. How do you find the vertex of the quadratic? There you go. What's actually calculating? X equals negative b all over 2a. What is that giving you on the graph? Well, it's giving you the x-coordinate of the vertex. It's actually giving you a line. It's giving you the axis of symmetry, which goes through the x-coordinate of the vertex. So this is the axis of symmetry formula. Okay, so negative b, what is b? Four. Because it's actually not in standard form. It was x squared and x. B is the x, the linear term, coefficient. So it would be negative 4 all over 2 times what was a? It's negative 1. Negative 1. So that one, maybe at the beginning, you beneficial to put it in standard form. Y equals negative x squared plus 4x. So this is the a and the b easier. So it looks like our axis of symmetry is x equals 2. Remember that is a vertical fold line? So x equals 2. How can we find the y-coordinate? We don't need x of the vertex is going to be on that line. How do we find the y-coordinate? Well, it is. So if we do y evaluating x equals 2, we get negative 2 squared plus 4 times 2. What does that leave us with? Yeah, negative 4 plus 8, so 4. So the point is 2 comma 4. Is this a concave up problem or a concave down problem? Concave down. So we know that because A is negative. Alright. How do we go about finding the x-intercept? So if it is concave down, it's going to cross the x-axis. How do we go about finding the x-intercept? Zero for y, and then solve for x. And I have to do some factoring. I don't have much room here. Okay. 0 equals, let's work out the x. Factor that out, I get 4 minus x. Okay, so we can see, by using the 0 property, x equals 0, that's an intercept. What's the other one? X equals 4. We can also use symmetry, because we don't want, we have to know the other. It was 2 units away from the axis of symmetry to the other means 2 units away. And there's a graph. Okay, this is a quadratic, 4x minus x squared. But we're going to apply the power rule. Okay, and then what's the derivative? What's y timing be equal to? What's the derivative of 4x? 4 of the x. The 1 that multiplies with 4, which is still 4, and the x goes down to x to the 0 power. Yep. Okay, now we need what about negative x squared? Bring the exponent in front and decrease the exponent by 1. That's negative 2. Let me make this bigger. I can actually see what I'm pointing at. Oh, that's really big. So you bring the exponent down, negative 2, x to the what power? And decrease the 1 by 1. X, so the first power, negative 2x. Another way to write that is y prime equals negative 2x plus 4. And just so happens that I didn't delete that line, so it's already graphed for you. Yay! Okay, what is the derivative of my linear function, negative 2x plus 4? Y equals. Y prime is negative 2x plus 4. That's the next derivative. y double prime equals, okay, here, all includes negative 2. So the x, when you decrease the power, it goes x to 0. The derivative of the constant goes away, right? The constant disappears. What type of a line as y equals negative 2? I'm just saying not saying straight, right? It's horizontal, all lines are straight. Horizontal. No slope or zero slope. Like this. Okay, so remember we made some connections last time? At critical points, maxes and medians, there's something that happens on the derivatives graph. At this critical point, what's the slope of the tangent line? That's the slope of the tangent line when you hit a max, and you round to start heading down. 0. So the derivative, remember, is just the slope, it's representing the slope. So when we hit this maximum, our slope is 0. So maximums and minimums represent what on the derivatives graph? X-intercepts, because it's at 0. Right, because the slope is 0 right there. Then we talked about when the graph is increasing, I think the slope is as it's increasing. Positive. So that section until x equaling 2 is positive numbers. So it means it's above the x-axis. Then when the x is, the parent function is decreasing, the slope is decreasing. Negative. That's why the derivatives graph is negative numbers. That making sense? I'm going to use to, not today, a graph or a worksheet that you have to do a match up. If f prime is doing this, and f double prime is doing this. If f is doing this, then f prime is doing this. So I feel like fill in the blanks. So make sure it's straight in your head. Okay? Does this linear function, or the first derivative function, have any maxes and mins? No. So it's actually very good that we have a slope of 0. No, so we're going to make them touch the x-axis. No, on our x double prime or y double prime. No. The derivative or the slope is constant, right? Down 2 over 1, down 2 over 1, down 2 over 1. Since it is constant, that's why our graph is flat. Because the slope always equals negative 2. And is y prime decreasing or increasing? Decreasing, because the slope is negative, hence why this is underneath the x-axis. Okay, is that clear? Okay, we could do this last time. Let's look at what's from the parent function to the second derivative, skipping the first derivative. Let's look at what happens. Do you see anything? Any connections from the parent function to the second derivative? Yes. Exactly. Perfect. Good job. Next is concave down always. Yes? So concave down on our parent function, the second derivative will be negative wherever the parent function is concave down. If the parent function is concave up, and in that section where I'm concave up, the second derivative would have to be in the positives above the x-axis. So, okay, down that paper would be looking at, and not today, but coming up, you have to be matching those. So we have concavity relationships to where our second derivative's graph is. We also have relationships from maximums to critical points that create x-intercepts. So the slope is 0 when you're rounding maximums and mins. If we're increasing on the parent function, that means we're positive on the derivative. Decreasing means we're negative on the derivative. So we're going to discover when we polynomials, and we're going to discover what the derivative is to some trade functions. Line of x. Let's know what that looks like, right? Something that is pointing in your head. You know what it looks like. The parent function might equal sine of x. The period ends on the x-axis when we hit what value? 2 pi. So pi here in the middle, and pi halves, and 3 pi halves. Those are kind of the sections that we use to make intervals for our sine function. What's the amplitude of sine? 1, it goes down to -1. How does sine start? What's the sign of 0? 0. And it hits its maximum at pi halves. And it hits the x-axis again at pi. And hits its minimum at 3 pi halves. And comes back and creates one period by 2 pi. So here, we're going to discover what y prime, or the derivative of the sine function is. So pi and 2 pi, pi halves, 3 pi halves. Okay? I hope you all have pencils, because I want you to try to look at with your neighbor first. Thinking about what we talked about last time, I would probably start with our critical points, maxes and mins, and draw on a derivative graph what that represents. Then think about the increasing sections, what does that represent on the derivative? And the decreasing sections, what does that represent on the derivative? And see if you can figure out what graph or what's the derivative of sine by graphing it out. Work together, talk about it together, start with the maxes and mins, and do the intervals of increasing and the intervals of decreasing. So one thing we figure out which function is the derivative of sine. Yes, good job. Yeah, the zero is the easy part, right? Now look at the interval in which it's increasing. What is that going to be on the graph? What's that called? So the maxes and mins create what on the derivative graph? That's a step. When the derivative is steps. So if I accomplish it, you went up and then you round the corner, you get the slope of your pen. Zero. So then you round the corner and 0. So that means you're on the x-axis because your height is 0. Because the derivative is representing a slope. Here is 0 here. Here is not. And then the interval at which it's increasing the graph is the derivative graph is going to be positive or negative? It's going to be positive. Positive. And then when it's decreasing, the graph is, what do you think that's called? Good. I'm trying to figure it out. So, I like to always show my maxes and mins about the easy part in my opinion. So at pi halves and 3 pi halves, what have my derivative function? Yeah, x-intercepts. Okay, now, is there an intercept right here? No, because we know it keeps going like that, right? So this is not an x-intercept. But this section from 0 to pi half, what's going on with that? It's increasing. So our derivative is, if it's increasing, our slope is increasing. So it's positive if we're increasing. So I need to get down to the, because I have to be to the x-axis for this point, right? Yes, that was going down, that's not the point. This is all, even though this is decreasing, the point is it's positive. Now, between pi half and 3 pi half, I have to make it back to the x-axis. Okay, and the whole section here is decreasing, so where should I be? Negative, and I have to make it back to the x-axis, right? For my next 0. And then I start increasing after that 3 pi halves. So I should be positive again. What graph is that? Cosine. I'm a little out of my blue part. But yes, this is the cosine graph. So the derivative of sine is cosine. If y is sine, y prime is cosine. Okay? Okay, let's try reverse. If y is cosine, let's draw that graph. We now remember what it looks like roughly. We have pi halves, pi, 3 pi halves. I was going to write cosine, alright. 2 pi. Where does cosine start? At 1, so it's maximum, right? And then we have an x-intercept at pi halves, and another x-intercept at 3 pi halves. So we have to make sure we hit the minimum, go back up, and then hit another maximum. Okay, let's take some predictions. What do you think the derivative of cosine is going to be? Okay, let's look at our critical points and our intervals of increase and decreasing, and try to discover if we are correct. Okay, who thinks it's have it? Yeah. Okay, well. First one, your x-intercepts. There's actually 3 x-intercepts. Now there are 3 maxes and rooms. There's one on here, 2 of it. 1, 2, 3. Alright, yeah, way too far. Okay, we're only going to 2 pi, so maybe we're just going to have it in the board. Just the 2 pi. Good, so what's that called? That's it. Because it's flipped, right? The graph is right. And this graph flips. So it's not really cyclical, it's how do you do a vertical flip in our equation? A negative. I don't know if it's sine, but it's negative because it's flipped. Negative sine. Okay, so we actually discovered one sine was similar, but our maximum is we have 3 critical points. So we have 3 x-intercepts. And again, this interval that we're decreasing all the way to our next critical point has to be positive or negative. Negative, like so. And then our interval which we're increasing has to be positive. It has to come back around and hit our x-intercept. So 1 to negative 1. Y prime is actually not sine. It's very similar, but it's flipped. So it is negative sine. So here's something to remember. Whenever you're taking the derivative of a cone, it's negative. Like when we do secant and cosecant, tangent and cotangent, the co's create a negative, okay, in the derivatives. Right, so sine, or the derivative of sine is cosine. And then we'll just give it up. The derivative of cosine is negative sine. Okay. These are all called transcendental functions. It says that down below. Because if it's typical polynomial, it's called transcendental. So another example of transcendental is our y equals e3x. We've done this graph before this year. What's the critical point on y equals e3x? 0, comma 1. 0, comma 1. Oops, too many parentheses. 0, comma 1. And it grows, right? And we have a horizontal asymptote. Okay, let's try to find the derivative of e to the x. So what you're saying is this decreases the whole time. Is that right? Alright, are there any maxes or mins on the exponential graph? No. So that means that we do not have what on our derivatives graph? No x-intercepts. Is this function increasing or decreasing the whole time? Increasing. So where's the graph going to have to be for the derivative? Positive. That's above the x-axis and it never crosses the x-axis. This is the derivative. It's what? It's the same thing. This is a nice one. The derivative of e to the x is itself e to the x. It has to be above the x-axis because it's increasing the whole time. So the derivative has to always be positive. And there's another relationship I just thought we should probably talk about. Let's look back at cosine and sine. At what point, if you're traveling along the wave of cosine, are you going to have the steepest slope? By half, right? Right here. Where's the slope go? Is it positive or is it negative? Is it negative? So this is going to be the lowest point in the negatives, right? And then we had another really steep point right here, 3 by halves. So it would be the highest peak. So there's another relationship. The x as long as you have it shifted, it can change if it's been shifted. But we should probably not say the x-axis, what we should say is the point of inflection. That's what it's changing concavities. It's changing from being concave down to concave up. You see those changes in concavities? Here's a crayon. Concave up, concave down. Where it changes concavity is point of inflection. That's where it's going to be the steepest. So that will create on the derivative the minimums and maximums depending if we're currently going down or if we're going up, or changing from concave down to concave up, or vice versa. Okay, so another connection there. The steepest point between the concavities is called the point of inflection that creates the maximum and the derivative. Okay. Okay, one last one. This graph right here, the f of x graph, we will see the piecewise function. It doesn't follow a typical polynomial function. Can you graph that one? The derivative of f prime. Knowing that derivative represents what? The parent function. Slope. But they're all linear. So you should be able to find the slope. So that's increasing, so you should be positive for the first section. Okay, let me help you out with the first section. And then you can probably pick it up from there. The first piecewise here from x is 0 to x is 3. What's the slope of that linear chunk? Y is on the left, right? What is it? 1. How do we graph y equals 1? Actually, yeah, a different one there. Erase what I just said. It is not, that's true. The very last sentence I just said. There is our maximum. 2, 3 to 6. And now our slope is 0. So on our graph, from 3, 4, 5 to 6, our slope should be 0. Okay? And this section right here is increasing, correct? So it should be positive. And what was from here to here, how many did we change? Okay, so we should make sure we're where on the x-axis. Yeah. Okay, now keep figuring out the last pieces. line, this blue line, is y equals 1x plus 0, right? So the slope is 1, the derivative is 1. So yeah, we need to just do a constant line, where the slope is 1. What about the slope at this point? What is, I have it on my notes here. What is the slope at this point? Is it 0? There's no slope at that point. In our next lesson on P2, we're going to be talking about points where you cannot take the derivative. This happens at corners or cusps. We'll talk about those on our next, we might get to today, I don't know. Okay? So here at 6, can we take the derivative right here? We know the slope of this point. Well, the reason is because the limits coming from both ways, well, the slopes, coming from both ways are different. So it's not the same slope. So at 6, we have an open circle as well. Okay? What's the slope from here? 6 to x equals 8. Down 3 over 1, so that would be what slope? Negative 3, which is going to be down here constant from negative 3, open circle, to 8. And is it supposed to be in the negative area? Yeah, why? Because the negative slope is decreasing. And then, the increases are going to be in the positives. And what's the slope from there to there? That's at 10. I think it's up 4 over 2, so it looks like it's 2. Okay? Alright, continuing with this idea of wind, we can take derivatives when we can't. Move on to tree 2 and say the last 10 minutes for the questions you still have on tree 1. So 5, 6. What's that row? Okay, I have this one up yet. When you choose to leave the new assignment log? You have one? Earlier? Okay, so begin with 3-2, differentiability. A function is differentiable as long as the domain is continuous. Okay, is continuous at every point on its domain. So we're talking about continuity, continuous, and differentiable. If both of those check off, that the domain is continuous, and every point along the domain is differentiable, then that means we can take the derivative. Versus, if that doesn't happen, then we probably have non-continuous points. Okay, so to determine if you can find the derivative at a given point, ask these questions. Is the point in the domain? Ask in the domain and you take the derivative. Okay, secondly, is it continuous at that point? So, we wrote this once today, those two in the hall. Didn't sketch it down, but what are the 3 rules to be continuous? Have the 3 exist? Between where the x is go and where the C's go. And then the last one is just hovers of being engraved in your head. Good, they're equal to each other. Excellent. Okay, so this is required as well. And is the function differentiable at that point? So here are some examples of what is not differentiable. You can have no corners. That's what we just had on that last one. No corners like that. So that corner is not differentiable because the slopes approaching from both sides of that corner are different. Okay, you can have no cusps. It's kind of like when two curves come in a bird. Two curves come together, that point where they come together, the wings of the bird, it's a cusp. Yeah, it's like a seagull if you were doing like elementary drawing. Okay, go vertical tangents. And no discontinuities. Okay. So those are things to watch out for. So, number one, say the domain of the function. Identify whether the function is continuous or differentiable. Remember, domain is for the x's. So all x values of this graph from negative infinity to positive infinity are all x values represented.
Yes.
JK, yes. Why is x equaling 2 in the domain?
Because
The point above it. Okay, and with the arrow, the means goes on forever. So the domain is negative infinity to positive infinity, or you can say reals. Okay, those are three options for domain. I usually remove the quotation most of the time, but you should probably be familiar that it also means all reals, meaning all real numbers. Okay, let's now write the interval of which is continuous. Is it continuous everywhere? No. Where is it not continuous? X equals 2. You can see that with the old school definition of continuity of where I have to look at my pencils, keep going. You cannot write that on your AP test. You must be able to prove that by one of the rules of continuity fails, at least one of them. Okay, so let's write our interval of continuity. That's our lowest bound. Negative infinity. Everyone negative infinity? No, we died first, right? So it's a parenthesis. And then it stays continuous until you get to which x value. So we're the spread, the 2. What should I put on the 2? Parenthesis, because it's not continuous at 2. But then yeah, good. Then we have another section that's continuous starting at which x value? 2. What should I put on the 2? Parenthesis, 2. Infinity. Okay? So we have a point of discontinuity because there's a hole. This right here is the hole is a point of discontinuity. So it's discontinuous right there. Okay? Yeah, so now for the interval at which we're going to take a derivative, what's differentiable, what x's fail, we cannot take a derivative right there. 4. Why? Cusp. So it's not, we have a cusp, so it's not differentiable. Where else? 2. Why? Exactly, because it's a discontinuity, right? Do you understand that again? You know discontinuities. What are 3 types of discontinuities? Whole, infinite, meaning like a vertical asymptote. Okay, so good. Actually 2 this time. So this, actually the 2 is both a problem that it's a discontinuity and as a point which are not differentiable. So it's not differentiable by number 4 on our list. Okay, so you write the interval at which we can take the derivative. Okay, negative infinity to what? 2, like we're going to 2. Parenthesis, union, parenthesis, to 4, because we have another issue at 4. Union, 4 to infinity. So our continuous interval in our domain is completely different than our interval that was differentiable, right? Okay. Well, you let's try number 2. Write the domain, write the intervals in which we're continuous and differentiable. So continuous has to meet those 3 criteria listed number 2. Differential has to reach the 4 criteria listed number 3.
Okay.
I think it's 7. Sorry. Okay, who has the domain now? Let's write on the board. Okay, let's see what you got. That's good. Now I've got continuous. Okay, let's look at what I have. At infinity to infinity or to 0, meaning 0 to 5, meaning 5 to 7 with a closed bracket on 7. What do you think about that? Yes, because we have to fill a very obvious fill-in point. At 7, I would agree with that. Any questions about the domain? Okay, who has the continuous? That's not continuous. Continuity. Interval at which it's continuous. Okay, let me pick someone. Do you have a pen? Okay. Read it. In this case, yes. Not always, but in this case, yes. But, like a reverse cubic, and then we cubic, and then just spread out whatever, just slowly. What's the color has? Thumbs up, middle, or down? Degree, minus, not. I think it's good too. Now in this case, the domain and the continuous intervals are the same. Okay, why are they the same? Versus number one, they weren't the same. Because in this one, we have the whole, number one, and the whole, it was replaced with, it was removed, right? Replaced with a point. So that x equals 2 is covered in the domain. So this whole doesn't have a replacement, right? Yeah. But 7 be continuous? So we stop at 7, and we have a floating point, so yeah, you put it back in. Okay. What about our differential? What do we define? What terms of the derivatives? How can I say differential? Okay, negative infinity to 0. We have a change here. Why is 4 important? After cuts. I'm just talking about the cuts. Good. Doesn't affect the continuity, right? But doesn't affect differentiability. Union 4 to 5, union 5 to 7 bracket. Okay? Good. Okay, let's stop there with 2.2. Would you pull out 3.1 for any questions? You're probably still more comfortable now with 3.1. Let me finish that. Grab some. Open up your books.